So now we're going to tackle the toughest of the friction questions, which is friction on an inclined plane. So we have a mass that's sitting on a ramp, so the plane that it's sitting on is inclined, and then there's a force that's on an angle with respect to the inclined plane. So this is friction part C, the third practice problem in your the handout, and this is going to take a few pages for me to solve while explaining how to do it. So be ready for that. How you note it down yourself, what I would recommend is you watch the video, make a couple little notes on the side of your handout or even on a scrap piece of paper, and then try the question yourself separately without the video, or at least have the video available, but try not to use it. See if you can solve this yourself. So here we go. You can pause the video and read the question right now on your handout. I'm going to start, and there will be several points in here where I'm going to pause things to shift around. First thing we do in any physics problem, following the 7-step method, is we determine what our target is. This is our target right here. Acceleration equals something meters per second squared. Now I didn't put a vector sign on this because right over here it says as it moves up the ramp. So what we're going to say is that up the ramp is positive and down the ramp is negative. And that means going along the plane of the ramp upwards. So let's draw on our values. Let's draw on our forces. The forces that we're given, well, we're given the push force, Phil's push force, and then the rest of the forces we have to come up with ourselves. So looking at this on an inclined plane, we know that it's on Earth, so it's going to have a force of gravity. So what everybody comes up with first. And that's going to be equal to mg. I'll just draw that in because this is part of our given and preparation. Another force that's happening here is the normal force. Now remember, the normal force does not necessarily work straight opposite gravity. The normal force is a force that's perpendicular to the surface of contact and away from the surface. So the ramp is exerting a normal force on the box, and it's exerting it perpendicular to the ramp. So there's the normal force. Another force that we have here, if the box is trying to move up the ramp, it's trying to go that way, friction acts against that. So friction works this way. We're given a bunch of information. We're given that the kinetic coefficient of friction is 0.27. That'll be useful with our friction force. We're given the mass of the box. We're given the push force, which is already on there. We're given that this angle. Now, let's bring our axis set in here. All right. First thing we can say is the angle that Phil's push force makes with the ramp. So I've lined that up with the ramp. Let's pull that out. Whoops. Let's pull that out again. So the angle that surface, that push force makes with the ramp, so that's this angle here, is 25 degrees. Excuse me. And this angle here is 12 degrees. Excuse me. So, any other information we have there? 25 degrees, 12 degrees, the mass. I believe that's everything we know. And of course we know that G is equal to 9.81 meters per second squared. So how do we tackle this? Well, kind of key to this problem is our frame of reference. If we keep the frame of reference as it's drawn on the page, the problem we have is we've got it going at an angle, we've got forces all acting at different angles. What we want to do is think, which way is the object actually going to move? The object's going to move parallel to the ramp. And it's not going to move perpendicular to the ramp. So why don't we make those our axes? So basically what we're going to do is we're going to do what I did here. We're going to take this axis and we're going to turn it so that up and down the ramp is our x-axis and perpendicular to the ramp is our y-axis. So that means our normal force is completely in the y-axis, our friction force is completely in the x-axis, and our movement is going to be completely in the x-axis. So we've shifted our frame of reference to make this a little bit easier for us. The problem, of course, is we have two other forces, Fp and Fg, that are not in that plane. So that's two inclined forces acting on this problem. So I've revisited it up here. You can go back and pause and look at that video, or look at that diagram and see if you understand it. I've redrawn the diagram right here. Let's see if we can make this a little closer to, that looks about right. So let's redraw our forces in here. Now, on this one we have, I'm going to break each of these things up. We have a given Fn right on the y-axis. Okay, and it's going to be equal to all the forces. It's going to, well, we'll figure that out in a few minutes. We have force of friction on the x-axis. And then we have the force of gravity, which is acting this way. Let's do it like that. Let's do it as a solid line. And we have Phil's push force. Because we know that the only movement is going to be on the x-plane, and that in the y-plane there will be no acceleration, we want to turn our push force, Phil's push force, and the force of gravity into components that only act in those directions. So let's break the push force into its x component and its y component. So this is going to be Fpx and Fpy. And since this is a 25-degree angle, this is going to be Fp cos 25, and this is going to be Fp sine 25. Pause the video if you're not sure what I'm doing here. Pause it, have a look at it, see if you can break this down. Okay, so we now have an x component for Phil's push force and a y component for Phil's push force. We can do the same thing with gravity. We can get gravity's y component and gravity's x component. So Fgy and Fgx. And there's a little geometry trick here, because we need either this angle or this angle. And it turns out that this angle here is going to be equal to this angle over here. This is 12 degrees, as we got in the original question. So that tells us that this angle here is also 12 degrees. Now I'm going to challenge you, it's your choice, but I'm going to challenge you to pause the video right now and see if you can demonstrate that to yourself using right angles, triangles, similar triangles, whatever works for you. It's a nice exercise to do for geometry. I'm going to move on. So now what I have is a set of x and y components to these forces. The x components are in the direction of motion, the y components are in the direction of no acceleration. And I can draw them over here. On this axis, we have Fn, we have Fpy, we have Fgy acting the other way. And in the horizontal plane, we have Fpx. Fgx is going the other way. And the force of friction is going that way. So we have three forces on each axis. Now, coming back to our problem, we need to know acceleration. And really, we're looking at the acceleration in the x direction. So I'm going to write x just so it's clear to you. So the acceleration in the x direction is going to be F net x over the mass. This is the equation that's going to fill in our answer at when we reach the end. Now, F net x over m, so we need F net in the x direction. F net x is going to be equal to the sum of all the x components, x forces. So we're calling right positive. So positive is going this way. So Fpx is positive. Fgx is negative. And Ff is also negative. So presumably if it accelerates up the ramp, Fpx is going to be bigger than the other two combined. And we know FPX, or we can get FPX, FP cos 25. We know FGX, that's going to be, sorry I didn't fill those in for you, FGY is going to be FG cos 12. FGX is going to be, well, let's just put it down here, it's going to be FG sine 12. So we know that. So we have this value, we have this value, we need the force of friction. And the force of friction is equal to mu k times the normal force, which we don't know. Now the normal force is in the y-axis, so now we have to go and figure out the normal force. So let's jump forward another page. This is just so I have room to show you what to do. So here's the challenge. Now, we have to figure out the normal force, so we have to work with F net y. F net y is going to be equal to the sum of the forces acting in the y direction. The y direction is the same as the normal force, so it's going to be the normal force plus, Phil's push force is upwards. The y component of Phil's push force is upwards, so Fpy, and the y component of gravity is negative Fgy. Now you'll notice that I'm doing this a little bit different from what I did in class and with some of the previous examples. I'm putting the negative signs in now. This is an option. If you want to do this, this is fine. Just be careful that you're always consistent. So right now, this plus and this minus, and the plus implied out front here, those are telling us which direction these forces are acting. So they're saving us a little bit of bother potentially. Now what we also know is that F net y equals 0. So we really have 0 equals Fn plus Fpy minus Fgy. And if we rearrange this, we leave Fn on one side, and we get Fn equals Fgy minus Fpy. Now conceptually, pause the video right now if you can't figure out the algebra, look it through, make sure you can do that. But conceptually, if we look at the diagram here, if the net force, if the y component net force is 0, this one here, Fn and Fpy, should add up to Fgy. So Fgy is going to be equal to Fn plus Fpy. Let's check and see what that makes sense, that fits with what we got over here. Fgy minus Fpy is equal to Fn. So yeah, that works out. Alternately, if we move this value over to here, we get the same equation. So now, we have all the values we need. Excuse me. What I'm going to do is I'm going to take this, and I'm going to plug it back in, Fgy minus Fpy, into here. So, equals UK, which we know, times Fgy minus Fpy. And I'm going to plug this back algebraically. This is going to go over to here. So we're going to get, let's plug the formulas in for these guys. Equals Fpx is cos 25 minus Fgx, which is Fg sine 12. So that comes from here, and the first one came from here. Fgx minus UK Fg cos 12 minus Fp sine 25. Those ones came from here and here. So let's check. Fp is 185. Cos of 25 we can calculate. Fg is going to be mg, where m is 35 and g is 9.81. Sine 12 we know. Mu k is I forget what mu k is. Let's go back and take a look. Mu k is 0.27. Fp is 185. We have an equation where F net x is what we need to know, and we know the values of everything on the right side of this equation. So at this point, you plug in the numbers, pause the video, plug in the numbers, and we will see if we come out to the same thing. I'm going to pause it while I do the calculation. Okay, so when I punch the numbers in, I get a net force in the x direction of 26.711559 newtons. And then we want to take that, let's make this bigger so it's easier to write on. We want to take that and plug it back in here. So we get 26.71159 divided by the mass, which is 35. And we get an answer of 0.763187. And let's back up to take a quick look at significant digits. 35, so that's 2, 2, 3, 2. We've got to use 2 sig digs in our answer. So we're going to round this to acceleration x equals 0.76. Let's take it back to our initial part here, 0.76 meters per second squared. Now, as I said before, your job at this point is to pause the video, stop the video, whatever you need to do, and try this question again on your own without help. Work at it until you can do it and get the same answer without having to refer to the notes, this video, or anything. Good luck. We'll practice tomorrow in class.